All right, so I'm actually going to do this video from home. I actually scheduled a review. I scheduled a room down in the basement of the Benson, but no one showed up. So we're just going to do it from right here. Starting with number one, we had to name this crazy looking compound. If you take it step by step, it's not that hard. A good way to go about these problems is to first understand if your complex ion or if your coordination complex is the cation or the anion. And in this situation, it's the cation, and so we will name this as normal. We won't have to change our metal at all. So the first thing I see is ethylene diamine, so I'm going to put that, if it was me, I'd put it on a piece of paper. Okay, that one starts with E, so because we have to remember the alphabetical order for this stuff. Next one is amine, but there's two of them, so that's diamine. And remember, a common mistake is students will order it as, with the di, considering the di. That's not part of the alphabetical order that we do. We just talk about the amine. So diamine. So A, that's probably going to be our first one in our name. Then we keep on going. We see nitro. Okay, so that's an N. So that's probably going to be near the end. And then we have chloro. So it turns out to be diamine, chloro, ethylene diamine, nitro, cobalt 3. Remember 3 because nitro has a -1 charge, so does chloride. So in order for the coordination complex to have a +1 charge to counteract with the chloride outside of the coordination complex, you must have cobalt be 3+ in order for that to work. So that's that. Next one, we actually have the name, and we have to put it together in a Werner notation. So we see in our name, we got 2 amines, we got 2 bipyridines, and we got 2 cyano groups. We also know, because it says ferrate, that the coordination complex is the anion. Okay, and that's important to know because your potassium is going to be the counter ion, which is the cation. So it's ferrate, so that means it's iron. So you got Fe, and then the order doesn't matter when you're doing the Werner notation. So diamine was first, so you get 2 amines right there. You got bis bipyridine, so that's 2 bipi, and then you got dicyano, so that's 2 cyanides, and that's all you got to do, and you got that one pretty simple. You also know that because the cyanides are -2, you need this coordination complex to be -1 to counteract the K+ that's outside the coordination complex. So that means the only way to get that to happen would be make iron 1+. Okay. So going on into magnetism, remember ferromagnets. Those are the ones that affect your neighbor. We talked about that in class, and in the review, Corbin and Braden we talked explicitly about a chart like this, and we know that those are attracted by a magnet. Paramagnetic or paramagnetism does not have there's nothing going on between neighbors. The magnetic moments on adjacent atoms do not affect each other. But it is attracted to a magnet, so that's where that's coming from. The diamagnetic also does not affect the neighbors. Each atoms do not affect the neighbors, and they repel. If you remember the frog video from class, then you remember that they had a magnet and they were making that frog float up in the air. So for number 4, unique stereoisomers. So you have to understand what this Werner notation means, and you have to understand kind of 3-dimensionally what is the same molecule and what's going to be different. So some key things to do, and some I think hints to be able to do these types of problems is to keep one of your bipi groups in the same location and start moving other substituents around. Make the nitro and the chloro group trans, and then cis, and that's 2 stereoisomers. And you guys got to think of another one. And what you can do there is, because this molecule is chiral, you could just draw the mirror image of the molecule that you draw with the cis conformation, and then you draw the enantiomer, and then you'll have another unique stereoisomer. But that one's kind of hard to talk about, but it's kind of hard for you guys to visualize what I'm talking about. But if you just go in and you look to your book, go to your book and you can see examples of unique stereoisomers. For number five is kind of hard to talk about as well because it's very visual. Just if you're going to do an octahedral situation, just make sure there's no line of symmetry in any way, horizontally, vertically. It's important that you cannot cut that molecule in half and have it be equal on both sides. Just like when we talk about our hands, there's no way you can cut your hand and make it be same on both sides, and so that's why your hands are chiral. So I think that's all I'm going to talk about with number five. Number six is the spectrochemical series, and you had to rank those three of them in terms of how large of a photon, the highest energy photon that they could absorb. And so what's important to understand is the farther right you go on the electrochemical series, that means that the amount of energy that they can absorb is going to be greater. So if we look at the ammonia group is the highest of those three, and you look at it correlates with the largest amount of joules per photon. And then H2O is in the middle, and it gets the middle amount, and CRF6 gets the least amount. So that's the thing. That's the correlation. You just had to understand that correlation. And then it asks for the next part, which one is high spin and which one would be high spin out of those three. And remember, if you remember high spin, you had the d orbitals, and you had two different layers. And in high spin, those two different, layers were closer together. And when you were filling up your electron configuration, you would actually fill up the bottom, and then you would jump up to the top and fill up the top before you paired up the ones on the bottom. And that's high spin. Well, if you think about it, which one of these three would be most likely to exhibit high spin tendencies would be the one with the smallest gap. And the one with the smallest gap would be the one that absorbed the least amount of joules per photon. And we look in our answers, and we see that CRF6, 3-, is our best bet on that one. All right, so moving on to number 7. Number 7, we had to do a drawing. So again, it's kind of hard for me to talk about on a video like this without you able to see what I was drawing. So let's just talk about each one of the points. Anode, it says to label the anode and the cathode, okay? So in a voltaic cell, in all cells, at the anode, we will have oxidation, and at the cathode, we would have reduction. And that's just something that you just had to memorize, okay? So no matter what, you just had to have the right, let's talk about the voltaic. When the aluminum was being oxidized, you had to realize, okay, oxidized, that's going to be the anode. So wherever the aluminum is being oxidized, that's going to be the anode. And in voltaic cells, we know that the anode correlates with the minus sign, and the cathode with the plus side. In electrolytic, it's reversed. Cathode is minus, and anode is positive. And that was the memorized thing that you just had to know. All right, so that takes care of that first one. Then it says, which direction do the anions, the cations, and the electrons flow? So let's talk about the anions first. So you look at your salt bridge, and I want you to think conceptually. Let's talk about the aluminum being oxidized. So you have a plate, and the aluminum on the plate is being oxidized to Al3+. So the solution is becoming more and more positive. So what does that tell you about where the anion of the salt bridge is going to go? Well, if this side is becoming more positive, it's going to attract more and more negative. Okay, so the anion is going to actually go in towards the anode, where Al is being oxidized to Al3+. The cation is going towards the cathode for the exact same reason. Ag+ is turning into Ag solid. That is a reduction. There is less and less positive charge there. So what's going to happen is the cation is going to want to come in and replace that positive charge in that solution. And the electrons will flow. They will flow towards the cathode. They will always flow toward the cathode because that's where reduction is happening. That's where a ion is being reduced to its solid form, and that requires electrons. Number 2, identify chemicals as well as their concentrations needed to construct your cell. All right, and we kind of talked about that. So at the anode for the voltaic, it's Al3+ and Al, and so you can have a solution of aluminum nitrate. That's what was used on the key. and the same for silver nitrate. So that was really, you could have done anything as long as you made a viable salt. And then the balanced redox reaction, you just got to understand, okay, like we already talked about, the aluminum is being oxidized, and so it's going to be solid on the left, and it's going to go to Al3+. And then the silver is going to be reduced, so you have silver on the left, Ag+, and it's going to Ag. And just make sure that that's balanced, and you should be, and that was pretty straightforward. For the next one, we want to know the EMF of the voltaic cell at standard conditions. So you need to go to the chart, and you understand that the silver is being reduced, so it's going to go first, and the number was 0.799, and the reduction potential of the aluminum is negative 1.602, so you do 0.799 minus negative 1.602, and that gets you 2.461 volts. Straightforward, just plug and chug. The next one wants to know the if it was a 0.1 molar solution. Now this one, you have to use the equation that, I don't know what it's called, but you have E cell is going to equal to the E naught of cell minus 0.0592 over N, N being the amount of electrons that were transferred in the reaction, times the log of the, well, in this, it didn't really matter because they're both 0.1. Well, actually, no, it did matter. Because in the balanced redox reaction, you needed 3 Ag pluses, and so it's anode over cathode. So it's actually going to be 0.1 over 0.1 cubed. And that's log of 0.1 over 0.1 cubed. And once you do that computation, you're going to get 2.422 volts. For G, it wants to know the delta G in joules, and you just use the equation delta G equals negative NFE, N being the amount of electrons transferred, F being Faraday's constant, and E naught being the reduction potential of the cell, the EMF of the cell, at standard conditions. Doing that computation, you get negative 3 times 96485 times 2.461, and you get negative 7.12 times 10 to the 5th joules. So that takes care of that. For number 8, it was a computation, it was a calculation problem. And you start with 2.5 amp hours. And what you have to understand is 2.5 amp hours is equal to 2.5 Coulomb hours per second. With that, you can do dimensional analysis, and I'll just read this off to you. So you got 2.5 Coulomb hours per second, and then you do 3,600 seconds per hour. That cancels out your seconds and your hours, and then you're in coulombs. Then you do 1 mole of electrons per every 96485 coulombs, and that now you're in moles of electrons. Then you multiply by, for every 1 mole of Ag plus, 1 mole of electrons is transferred, and that's going to get you into moles of Ag plus. Then you say for every 1 mole of Ag plus, you have 107.86 grams of Ag plus, and that's from the periodic table, and that gets you 10.06 grams of Ag plus plated. And that's 8. Number 9 is a redox reaction you have to balance in basic conditions. And so this one, I made a key online with the kind of the intermediates or the kind of the basic steps. But first things first, on those, you're going to have to balance your, what I call the main element. And in this one, the main element is cobalt. And actually, we have a chloride ion. And you'll notice that you have to balance the chloride first. So you get 2Cl minus on the right side. Then you have to balance your oxygens with water. That's the key there. And then you balance your hydrogens with H+. However, it's basic, so when you add H+, you add also OH- in the same amount to both sides of the equation in order to get into a basic solution. At that point, you have to balance the charges, and you determine how many electrons you need to balance those charges. Then you look at the other half reaction, which we had a nitrogen oxide, and same situation. You balance the main element. We need 2 Na+. Then you balance your oxygens with water and your hydrogens with H+. But since it's basic, you add OH- on both sides in the same amount. And and you'll actually end up moving 2 electrons in that situation. So in order to get the electrons to cancel out, you multiply the first one by 2 in order to get both of those. So then you have 2 electrons on the left, 2 electrons on the right. Those cancel out, and you can begin to cancel out all of your other species to get your final redox reaction. So that's that. Really quick. The key's posted, like I said, and so feel free to go look through that and email the graders for clarification on point distribution. And but anyways, I hope that was helpful. I know it was kind of one of the more difficult tests to talk about on a video like this, but hopefully anything that was foggy was cleared up. But it's been a really awesome semester working with you guys, and I hope you guys just do really well in this final, really steady, and you guys be able to knock it out of the park. But that's all I got.